Okay, so in the remaining lectures, this lecture and the next one, I'm going to investigate the stability criteria for numerical schemes, especially focusing on finite difference schemes. Um, so, especially for space-time problems, and if you remember, we mostly focused on infinite difference. We talked briefly about initial value problems, the stability of those time marching methods. And now, what about if you also have space, space discretization? So, we are going to consider and investigate these space-time problems. So, consider partial u over partial t minus d partial square u over partial x square equals to 0. So this is our governing equation. Assume a constant spacing delta x and finite difference approximation, or FDA, for this equation can be written as ui n plus 1 minus ui n over delta t minus d, and the second term I'm going to use a second order center difference, ui plus 1 n minus 2 ui n plus ui minus 1 n over delta x square equals to 0. And this is an explicit Euler method, right, for time marching. So I can rearrange these terms and write ui n plus 1, which is the ui, the value of ui at the new time step, equals to, by rearranging the terms, I can get ui n plus d delta x, delta t over delta x square ui plus 1 n minus 2 ui n plus ui minus 1 n, all of them at the previous time step, okay? And then I will define this as a dimensionless diffusion, right? Because this is dimensionless. If you calculate it, it will be dimensionless. Because just very quickly, but for people who are familiar with dimensional analysis, so this, the left hand side has the if u is velocity, has the dimension of like the units of it will be meter per second, and so this term also has to be meter per second, the whole term. And because this is meter per second, so this term should be dimensionless. Okay, so it shouldn't have any dimension. So that is why we call this dimensionless diffusion. And another word, you can also notice that d, the diffusion parameter, it is L square over time, the dimension of that, and so when you multiply it by delta t over delta x squared, it will be dimensionless. So this was just a side note to illustrate why this is dimensionless. And so I can write ui at n plus 1 equals to d ui, dimensionless diffusion, ui minus 1 at n plus 1 minus 2 d ui n plus d ui plus 1 n. Okay, so this is the equation we have. So this equation is going to be stable, and we will show it later, if this dimensionless parameter is smaller or equal to 1/2. So this is a stability criteria for that. But what I mean by that mean, if your d is greater than that, then your solution are gonna blow out. Like as you solve u for the new step, it's gonna go to infinity. So ui n plus 1 is gonna go to infinity and is gonna blow out if you don't if the stability criteria does not hold. Okay. So this was just a brief example of what we are gonna do here, and I want to introduce a general framework for that, and what we call that is, this is a general framework for finding and solving these stability problems, and that is called Fourier analysis for stability. Okay, let's see what it is. So we have Fourier series. So Fourier series is fx equals to a0 over 2 plus sigma k equals to 1 to infinity of ak cosine k pi x over L plus bk sine k pi x over L. This is the Fourier series for x between L and minus L. Okay. This means that we can represent any function using this Fourier series and these coefficients a, k, and bk, any periodic function, of course, and in this form. And in the complex form, let me show this in the complex form. So in the complex form, this will be, we define e to the I plus minus I theta as, so this is a definition from complex algebra, cosine theta plus minus I sine theta, where I is imaginary number. I is square root of minus 1. Okay? Or I square is minus 1. This is an imaginary number. So based on this, we can say that cosine theta is 1/2 e I theta plus e minus I theta, and sine theta can be represented as 1/2 e I theta minus e minus I theta. Okay, just look at this definition here, and then you can write this based on that. Okay, very simple. And then we substitute this into Fourier series, and what you get finally is this. Fx in the complex form can be represented as sigma k from minus infinity to infinity of ck e to the power I beta k x, where from here, look at that, where C0 is A0 half and CK is 1 half AK minus IBK, and C minus K is AK plus IBK over 2, where BK, beta K is K pi over L, and wave number is defined as 2 pi over LK, where LK is wavelength. Okay, so this is the definition of beta K here. And these CKs are based on this, the original Fourier series, right? Those coefficients, what are the relationship between those coefficients are shown here. So in general, this is the thing that you need to remember, because this is what we are going to use mostly, which is the Fourier series in complex form. Okay, so now I want to make some remarks about that. First, how we should do this Fourier series analysis, okay? So this was just an introduction of Fourier series and what does this mean and how does this look like. So the first thing you need to do is, in this analysis, is to represent initial condition by Fourier series. That is, you say U0, U at time 0. We can just represent it with sigma CK EI sigma KX. So this is the first thing. You represent the initial condition by Fourier series, and I'm gonna go through an example for that, but this is the general approach that you need to take. And then initial condition is propagated by the finite difference approximation, or FDA. We are going to propagate it in time by using these finite difference approximations that we have, and we want to investigate it by the finite difference approximation, in which we want to investigate its stability, right? So this is again to assess the stability of these finite difference approximation discretizations, okay? Then the FDA is the same for each time step, right? It's not gonna change as you change the time step. It's gonna be the same thing. You are not going to change your spatial discretization at later times, right? You are going to keep the same discretization that you already had at the beginning. So the solution of any time Tn can be expanded using Fourier series. Okay, at any time we can expand the solution by using Fourier series, and we are going to go through that. And for linear operators, each component of the Fourier series is propagated independently. Okay. And the other remark I want to make is at t0, which is initial time, initial condition, u0 can be represented as sigma k ck e I sigma k x. Then at t1, which equals to t0 plus delta t, u1 can be represented as sigma k dk e I sigma k x, which equals to sigma k. This is going to be a different coefficient, right? Because at that time the your u1 is going to be different. So we can write it as dk over ck times ck ei sigma k x, which again we can write it as sigma k lambda k times ck ei sigma k x. Okay, so at tn un can be written as sigma k lambda k to power n ck ei sigma k x. Okay, this is how it propagates in time. And so for stability, we require lambda k to be smaller or equal than 1, right? For all k. And lambda k is known as amplification factor. Amplification factor. So what I mean by that, look, if your lambda k is greater than 1, look at this equation here. Let me highlight that. If your lambda k is greater than 1, your un, the limit as n goes to infinity, as time goes to n, un is gonna also go to infinity, right? Because lambda is equals to kind of lambda k to power n, and lambda k is greater than 1, so it's gonna become infinity, right? So the stability criteria says this lambda k should be smaller or equal than 1. And this is how we are going to investigate the stability of finite difference approximation using this Fourier analysis theory. So I'm going to give you an example for this in the next lecture. But just briefly, let's review what we did. We just introduced this Fourier series, the general formula of Fourier series for any periodic function by this definition of ei theta. Then I wrote this Fourier series representation in complex form, which is shown here. And if you remember, we had this complex Fourier integrals, so it's very similar to that, but now it's a series rather than an integral. This means it is discretized. Previously in the lectures that we had before, it was an integral form because we were solving it in continuous form and we wanted analytical solutions. But here we want numerical solutions which are discretized, and so we are going to use discretized or series, Fourier series rather than Fourier integral transforms or Fourier integrals. So then I talked about the general way of dealing with this Fourier series analysis, and this is kind of a summary of that. At time equals to 0, you have the initial condition, and then you propagate it in time. And so this is going to be the propagation in time, where lambda is an amplification factor, which is just the coefficient at the new time step, or dk, over the coefficient at the previous time step, or ck, okay? From the initial condition, which is going to be ck. So it's like lambda k to power n, and then for the stability to hold, we need this lambda k to be smaller or equal to 1, and this is the stability criteria for that. So next lecture, I'm going to solve some examples of this strong method for finding the stability of finite difference approximations. Thank you very much, everyone.